Somewhere inside a supercooled laboratory, kept colder than the far reaches of outer space, a machine is trying to think. It is not thinking the way you are thinking right now, in language and memory and the continuous, messy flow of human experience. It is thinking in quantum states, in superpositions, in the finest grained language the universe has for describing what exists before anyone looks. And it keeps making mistakes. Those mistakes are the subject of one of the most serious, technically demanding, and philosophically loaded scientific efforts of the past several decades. They are the reason quantum computers, despite decades of theoretical development, have remained frustratingly fragile. They are the reason the world's most powerful technology companies have spent billions building refrigeration systems, control electronics, and error suppression architectures, just to keep a small number of quantum bits stable long enough to run a meaningful calculation. And they are the reason that, in November 2024, a team from Google DeepMind and Google Quantum AI published a paper in the journal Nature describing a system called AlphaQubit, a machine learning decoder built on the same transformer architecture that underpins the world's most powerful language models, that looks at quantum errors differently than anything that came before it. What AlphaQubit found in that error data is not what the headline version of this story usually claims. No single experiment secretly rewrote physics. No hidden message was found waiting in the noise. The reality of what happened is stranger and more significant than that. Because what AlphaQubit demonstrated, in practice, on real hardware, is that the errors generated by a quantum processor are not random. They are structured. They have patterns. They carry the fingerprints of physical processes occurring at the deepest level of matter. And a sufficiently powerful machine learning system trained on hundreds of millions of examples of those errors can learn to read those fingerprints and use them to reconstruct what actually happened inside the quantum system better than any algorithm human physicists have yet designed. That result, published in Nature and confirmed on real hardware at Google's Sycamore quantum processor, is technically precise and scientifically verified. But it opens a door to something far larger. To understand what is genuinely at stake, you have to go back almost 100 years, to a moment when physics looked at matter closely enough to discover that the universe, at its foundation, does not behave the way anyone expected. In 1927, at a conference in Brussels, attended by nearly every major name in theoretical physics, the world's best minds gathered to argue about what quantum mechanics actually meant. They had the equations. The equations worked with a precision that still, to this day, has not been matched by any other scientific framework in history. Quantum mechanics predicts experimental outcomes with extraordinary accuracy across a range of scales from the behavior of individual electrons, to the structure of chemical bonds, to the properties of materials used in every semiconductor device ever built. Nobody was disputing that. What they were disputing was what the equations meant about the nature of reality itself. The core problem, still unresolved, still argued about, still producing papers in philosophy journals and physics journals, and the contested territory between them, is this. Before a quantum system is measured, the mathematics describes it as existing in a superposition, a combination of multiple possible states simultaneously. An electron does not have a specific position. It has a probability distribution across many positions at once. A quantum bit, a qubit, does not hold a 1 or a 0 the way a classical computer bit does. It holds both simultaneously in a weighted combination that only resolves into a single definite answer the moment a measurement is made. And here's the part that nobody has ever been able to fully explain. The act of measurement itself, the moment of looking, collapses that distribution into a single outcome, instantaneously, irreversibly, without any mechanism provided by the equations that describes how the collapse happens. Werner Heisenberg called this the Copenhagen interpretation. In its most practical formulation, it says, stop asking what the particle is doing between measurements. You can only know what a measurement yields. The universe, at its foundation, is probabilistic. There are no hidden gears turning underneath that would reveal a more classical picture if only you could zoom in far enough. This is what is real. Hugh Everett disagreed. In 1957, as a doctoral student at Princeton, Everett proposed what he called the relative state interpretation, later renamed by the physicist Bryce DeWitt as the many worlds interpretation, which dispensed entirely with the collapse of the wave function. In Everett's framework, the wave function never collapses. Every time a quantum measurement occurs, the universe branches. Every possible outcome of every quantum event is realized simultaneously in a continuously expanding tree of diverging realities. There is no collapse, because there is no need for one. Every branch simply continues to exist, running in parallel, forever separated from the others by a process called decoherence. Bohr and his collaborators rejected this idea entirely. Everett, deeply discouraged by the reception, left academic physics not long after and never returned. The many worlds interpretation spent decades as a minority position, viewed by most working physicists as an untestable, metaphysically extravagant solution to a problem that Copenhagen simply avoided by refusing to ask. And then, in 1985, a British physicist named David Deutsch connected the many worlds interpretation to a new idea that would eventually change the history of computing. Deutsch proposed the concept of a universal quantum computer, a machine that, unlike any classical computer, could exploit quantum superposition to hold and process multiple states simultaneously. In Deutsch's interpretation, the power of quantum computation was not just a mathematical convenience, it was evidence. A quantum computer performing a calculation faster than any classical machine was, by his reasoning, processing information across multiple parallel branches of the wave function simultaneously. The exponential advantage that quantum computers could theoretically offer was not coming from nowhere. One interpretation of that advantage is that it is borrowed from worlds that exist in parallel with our own. This is a minority view, and Deutsch would be the first to stress that it is an interpretation, not a settled physical fact. Many quantum computing researchers work every day without adopting or requiring the many worlds picture. But it is also not a fringe claim. It is a serious, mathematically rigorous position defended by serious physicists, and it has resisted all efforts to be definitively disproven. When Google's Hartmut Nevin, the leader of the quantum AI team, commented publicly on the Willow chip's results in December 2024, he did not shy away from this interpretation. In his view, the extraordinary computational results produced by the chip, a benchmark calculation completed in 5 minutes that the world's fastest classical supercomputer would require 10 septillion years to match, were consistent with the machine performing computation across multiple branches of reality simultaneously. Scientists like astrophysicist Ethan Siegel and many others have pushed back on that framing, noting that the benchmark in question is not a practically useful calculation, and that quantum phenomena like superposition can be interpreted through the Copenhagen lens or pilot wave theory without invoking a multiverse at all. The debate is genuine, ongoing, and unresolved. What is not in dispute is that the Willow chip in December 2024 became the first quantum processor to demonstrate below-threshold error correction, meaning that as the number of physical qubits in the system increased, the error rate in the logical qubit did not grow. It shrank. The system got better as it got bigger. That result had been predicted theoretically for nearly 30 years. Nobody had convincingly demonstrated it in practice until Willow. Understanding why that matters requires understanding what quantum errors actually are. And this is where AlphaQubit enters the story directly. A quantum computer does not work with bits the way classical computers do. Classical bits, the ones and zeros inside every laptop and server on the planet, are robust. They can be copied, checked, and corrected trivially. A 1 stays a 1 until something explicitly changes it. Quantum bits cannot be copied, a consequence of a mathematical result called the no-cloning theorem. They cannot be directly measured mid-computation without destroying the quantum information they hold, and they are extraordinarily sensitive to their environment, to heat, to electromagnetic fluctuations, to vibrations, to the simple passage of time. Any interaction between a qubit and its surroundings causes decoherence, the gradual bleeding of quantum information into the environment, effectively transforming the delicate quantum state into classical noise. Even at temperatures colder than deep space, even in the most carefully engineered superconducting circuits on Earth, quantum errors occur constantly. The standard solution to this problem is called quantum error correction, and it works by encoding a single logical qubit, the unit of quantum information you actually care about, into a lattice of many physical qubits. The original version of this idea was formalized by Peter Shor in 1995, who showed that, in principle, quantum error correction could protect quantum information indefinitely against errors below a certain threshold rate. The key word is in principle. Actually, implementing error correction efficiently in hardware has been one of the defining engineering challenges of the field ever since. The surface code, which became the leading approach to quantum error correction over the past 2 decades, works by arranging physical qubits in a 2-dimensional grid. Data qubits hold the information. Ancilla qubits perform what are called parity checks, or stabilizer measurements. They repeatedly probe the relationships between neighboring data qubits without measuring the data qubits themselves, in a careful quantum way that preserves the encoded information while producing a running record of any errors that have occurred. The sequence of these parity measurements over time is called the error syndrome, and the syndrome is what a decoder has to interpret. The surface code belongs to a family of topological codes, meaning it exploits the global non-local structure of a 2-dimensional qubit lattice to protect information against local errors. An error that affects a single qubit changes a local pattern of syndromes. An error that would corrupt the logical qubit requires a chain of errors stretching all the way across the entire lattice, and the probability of that happening decreases exponentially as the lattice grows larger. This is the mathematical guarantee that makes the surface code so attractive. Bigger really is better. provided the individual qubit error rate stays below the threshold at which adding more qubits helps more than it hurts. The job of a decoder is to read the syndrome, a string of signals indicating where parity checks have changed unexpectedly, and infer from that pattern which physical errors most likely occurred, so those errors can be corrected before they propagate into the logical qubit. Decoders are the critical bridge between the quantum hardware and reliable quantum computation. For 30 years, the field relied on classical decoders built on mathematical optimization techniques, the most widely used being minimum weight perfect matching, which models the decoding problem as a graph and finds the most likely error configuration efficiently. These methods are fast, they work, but they have a fundamental limitation. They are built on explicit mathematical models of how errors occur, models that are necessarily simplified compared to the actual, highly complex correlated noise that real quantum hardware generates. Real quantum hardware does not produce idealized independent errors. It produces crosstalk between qubits, leakage events where qubits escape their two-level subspace into higher energy states, correlated errors that ripple across multiple qubits from a single physical disturbance, and readout errors in the measurement process itself. A mathematical model built on assumptions of simple independent errors does not capture this. It leaves accuracy on the table. And accuracy in quantum error correction is everything, because the entire edifice of fault-tolerant quantum computation depends on the error rate per logical operation falling below a threshold level. Miss that threshold, and the error correction adds more errors than it removes, and the system becomes useless at any scale. This is the precise problem AlphaQubit was built to address. The paper published in Nature in November 2024, authored by Johannes Bausch and a large collaborative team from DeepMind and Google Quantum AI, presented a recurrent transformer-based neural network trained not on a simplified mathematical error model, but directly on syndrome data generated by real hardware. First, the model was pre-trained on hundreds of millions of synthetic syndrome examples, generated by computer simulation, giving it a broad foundational understanding of what error patterns look like across a wide range of noise conditions. Then, it was fine-tuned on experimental syndrome data from Google's Sycamore quantum processor, real parity check measurements from real physical qubits with all their hardware-specific quirks, correlations, and noise structures that no idealized model fully captures. When tested on new Sycamore data, AlphaQubit set a new benchmark for accuracy. It made 30% fewer errors than correlated matching. The widely used decoder it replaced is the state-of-the-art, and 6% fewer errors than tensor network methods, a more exhaustive classical approach that is computationally too expensive to run in real time, but has served as the theoretical ceiling for decoding accuracy. AlphaQubit matched that ceiling in practice, on real hardware, while running at speeds practical enough to be deployed alongside an actual quantum processor. The improvement is not marginal. In a domain where error rates determine whether fault-tolerant computation is achievable at all, 30% is a significant stride. But here's the detail that carries the deeper implication. The reason AlphaQubit outperforms mathematical decoders is not that it has better mathematics. It is that it has no explicit error model at all. It has patterns. It learned from hundreds of millions of examples what syndrome sequences look like when particular categories of physical error have occurred in the underlying hardware. It built a statistical map of the relationship between syndrome signals and actual errors, a map that implicitly encodes the real, correlated, hardware-specific noise structure of the Sycamore processor in a way that cannot be written down as a simple set of equations. The implications of that, when unpacked, are not trivial. The syndrome data produced by a quantum processor is a record of what the hardware's environment has done to its qubits during a computation. Every time a qubit interacts with a stray photon, every time thermal fluctuation nudges a superconducting loop, every time crosstalk between neighboring qubits introduces a correlated phase error, that event leaves a trace in the syndrome stream. The syndrome is not noise. The syndrome is signal about what the physical world did to the quantum world at a scale of interaction so fine that classical physics has no language to describe it accurately. What AlphaQubit learned to do was read that signal more faithfully than any hand-engineered algorithm had managed before. There is a word for what a transformer model does with sequential data of this kind. It finds structure. The same architecture that taught language models to recognize the deep patterns governing how words and sentences in human language relate to each other was applied here to the patterns governing how quantum errors relate to each other across space and time. And the structure it found was there to be found, because the physics of quantum error is not random. It is governed by specific mechanisms, specific interaction types, specific coherence timescales, and specific environmental coupling effects that follow rules. AlphaQubit learned those rules empirically from data, and outperformed every decoder that tried to encode those rules mathematically from first principles. Researchers following this development at institutions including Delft University of Technology's Q-Tech division have called this result a notable step forward in making quantum computing viable for practical applications. The specific phrasing matters, not a curiosity, not a theoretical advance, a step toward viabilities, meaning toward the day when quantum computers can solve problems in chemistry, materials science, drug discovery, and cryptography that classical computers cannot practically address. The timeline for that day, which researchers had for years framed in the language of distant decades, has been revised. Estimates from multiple groups now suggest a useful, error-corrected quantum computer capable of meaningful practical computation could emerge within the next 10 to 20 years, depending on how steadily the engineering advances. That revised timeline, however, raises a question that has been quietly growing in intensity alongside the hardware progress, the same question that divided the room in Brussels in 1927. What is actually happening inside a quantum computer when it operates? When you run a calculation on a classical computer, the answer is unambiguous. Electrons flow through circuits. Transistors open and close. Bits flip between states. Every step can in principle be traced, observed, and understood through ordinary physics. Nothing mysterious occurs. But when a quantum computer runs a calculation, it does so by placing qubits in superposition, a state that is genuinely not any single value, but a combination of values, each weighted by a probability amplitude. The computation evolves through interference between those amplitudes in a way that uses the structure of the problem to amplify the probability of the correct answer. The final measurement collapses the superposition, producing a classical output. Something happened between the beginning of the computation and the end, something that, in certain interpretations of quantum mechanics, involved processing information in a space vastly larger than the physical space of the processor. The many worlds interpretation says that something was a branching of reality into superposed computational paths that interfered with each other before converging on an answer. The Copenhagen interpretation says that question is physically meaningless. The mathematics works, the answer is right, stop asking what happened in between. The pilot wave interpretation, developed by David Bohm, says there are hidden variables guiding particle trajectories that produce the same statistical results without requiring either collapse or branching. Each of these frameworks makes the same experimental predictions. None of them can currently be tested against each other by any known experiment. AlphaQubit does not resolve this debate, but it sharpens it in a way that the researchers behind the project are careful to acknowledge and that commentators sometimes conflate with a much stronger claim. What AlphaQubit demonstrated is that the errors produced by a quantum system have learnable, physically meaningful, structured content that reflects the detailed mechanics of quantum hardware interacting with its environment. The model did not discover this structure by consulting a physical theory. It extracted it from data, the way a sufficiently powerful pattern recognition system always extracts structure from data when structure is genuinely there. The fact that the structure is there, the fact that quantum error syndromes are not featureless noise but carry rich correlational information about physical events at the quantum scale, is itself a statement about the nature of quantum reality. Quantum errors are not random accidents. They are consequences. They have causes that operate according to rules, and those rules are recoverable, at least partially, from the record the hardware leaves behind. Some researchers suggest this line of reasoning is connected to a broader insight that quantum computing hardware is gradually making unavoidable. As quantum processors scale up, as the qubit counts go from dozens to hundreds to thousands to the millions that Google's own roadmap targets for full fault-tolerant computation, the error correction systems that keep them running will need to process increasingly vast streams of syndrome data in real time. Classical decoders will hit limits. Neural network-based decoders like AlphaQubit will need to scale with the hardware, and scaling them will require feeding them ever larger quantities of experimental syndrome data from ever larger quantum processors. The data those processors generate will contain, embedded in their error patterns, an increasingly detailed empirical record of quantum mechanics operating at a scale and precision never before directly studied. In other words, the error correction data is a kind of microscope. Every syndrome stream is a window into the specific physical events, the interactions, the couplings, the decoherence channels, occurring in a real quantum system at the boundary between the quantum and classical worlds. That boundary, sometimes called the Heisenberg cut, is precisely the location where the measurement problem lives. It is where the equations of quantum mechanics give way to the everyday, definite classical world of objects with positions and momenta and outcomes. And nobody has ever been able to say, from first principles, exactly where the cut is, or what physical process enforces it. One possibility, explored by theoretical physicists since the 1980s, is that there is no cut, that the transition from quantum to classical is not a fundamental discontinuity, but an emergent effect of decoherence, the entanglement of quantum systems with their environments on larger and larger scales, until the interference between different branches of the wave function becomes unmeasurably small, and the different possible outcomes of a measurement effectively stop interacting with each other. In the decoherence picture, the quantum world does not collapse into the classical world. It decoheres into it. The superpositions do not disappear. They simply become so entangled with so many environmental degrees of freedom that recovering them is practically impossible, not fundamentally forbidden. This is the picture most compatible with Everett's many worlds interpretation, and it is increasingly regarded as the most technically coherent resolution to the measurement problem available to date, even among physicists who do not endorse the many worlds ontology. What makes this directly relevant to AlphaQubit is the following. The errors that AlphaQubit decodes are, at a physical level, events of exactly this kind. They are decoherence events. They are moments when a qubit, carefully prepared in a quantum superposition, carefully isolated from its environment by superconducting circuits and dilution refrigerators and layers of electromagnetic shielding, nevertheless entangled with something it should not have. The syndrome record of those events is a record of decoherence happening in real time, in real hardware, captured with the fidelity that modern quantum processors can provide. And AlphaQubit learned to read that record with an accuracy that exceeded what human-designed algorithms had managed. Whether that pushes us toward Everett or Copenhagen or Bohm or some framework not yet invented is genuinely uncertain, and researchers are clear about that. The evidence does not yet allow a verdict. What it allows is a much sharper framing of the question. Because now, for the first time, there is experimental hardware that produces high-fidelity records of quantum to classical transitions at the level of individual qubits, at rates of millions of events per second, with the syndrome data preserved and analyzable. And there is a class of machine learning systems sophisticated enough to extract meaningful structure from that data. The combination is new. It did not exist 5 years ago. What it will eventually reveal, what deeper structure, what unexpected correlations, what signatures of the underlying mechanics of the quantum classical boundary, is not known yet. Google's roadmap from the Willow chip toward a fault-tolerant processor at scale requires reaching 1 million physical qubits and reducing logical error rates to less than 1 error per 10 trillion operations. To get there, researchers at Google Quantum AI have been explicit that better decoders are not the only requirement. The hardware itself must improve, the classical coprocessing infrastructure must scale, and the control electronics must become faster and more precise. Michael Newman, a research scientist at Google Quantum AI, described the below-threshold demonstration on Willow by saying simply, "We are finally below the threshold. The work has barely begun." Nadia Haider, a quantum computing researcher at Delft University of Technology's Q-Tech division, who wrote a companion perspective piece in Nature alongside the AlphaQubit paper, framed this result as a notable step forward in making quantum computing viable for practical applications. Language calibrated to convey significance without overclaiming. The emphasis on step is deliberate. The field has learned repeatedly that quantum computing milestones tend to open onto further requirements, rather than arriving at destinations. Below-threshold error correction does not mean fault-tolerant computation exists. It means the path toward it has been confirmed as physically accessible, which is different from having walked it. Still, the questions that path raises, as it leads deeper into the quantum regime, are not purely engineering questions. They are questions about what kind of thing the universe is at the scale where classical descriptions run out and quantum mechanics takes over without apology. A quantum computer operating at the fault-tolerant level will process information in ways that have no classical analog. The calculations it performs will involve superpositions across millions of physical qubits, maintained through error correction systems that continuously monitor and restore quantum coherence against the constant pressure of decoherence. The error syndromes generated by that process will constitute, in effect, one of the most detailed empirical records of quantum mechanics in action that has ever existed. What AlphaQubit found in the error correction data from a 49-qubit processor was structure sufficient to enable state-of-the-art decoding. What might be found in the syndrome streams of a million-qubit processor, analyzed by machine learning systems trained on years of experimental data, by researchers asking not just how to correct the errors, but what the errors are telling us about the physics beneath them. That is a question that does not yet have an answer. Some researchers suggest it could refine our understanding of decoherence timescales and coupling mechanisms in superconducting circuits in ways that feed back into hardware design. Others suggest it could eventually inform the ongoing debate about quantum interpretations by revealing empirical signatures that different theoretical frameworks predict differently. The evidence does not currently allow certainty about how far this line of investigation will go. But the uncomfortable, fascinating implication is already visible, sitting at the intersection of a transformer-based neural network trained on quantum error data and a century-old argument about whether measurement creates reality or merely reveals it. Every qubit that decoheres inside a supercooled quantum processor is, at some level of description, a small piece of evidence about what the universe does when nobody is looking. Every syndrome event that AlphaQubit processes is a window onto the mechanism, whatever the mechanism is, that transitions quantum possibility into classical fact. And the machine processing those events is, for the first time, good enough to notice things in that data that human-designed algorithms were not. What it notices, what patterns emerge at scale, what structure is embedded in the error streams of a quantum processor that no theoretical model has yet predicted or described. These are not currently answered questions. They are currently asking questions. And the unnerving part is not that the answers are unknown. The unnerving part is that the instrument being used to look for them is a kind of mind, learning, generalizing, finding patterns, pointed at the deepest, least understood seam in the fabric of physical reality. The universe has been generating quantum errors for as long as matter has existed. It has just never had anything patient enough and capable enough to look at all of them carefully and ask what they mean.